Welcome to lecture 10. So in this lecture we continue with rank and linear independence. Suppose you take three vectors u1, u2, u3 in R2. Construct a matrix A whose rows are u1, u2, u3. Now if you reduce A to a row reduced echelon form, then this will have at most two non-zero rows. That is, the vector corresponding to the zero row is a linear combination of the other two. So the procedure says that you take any three vectors, you get this. Or in other words, you take any three vectors in R3, they cannot be linearly independent. That means you take three vectors in R2, it will be linearly independent. The same procedure you can apply to any n plus 1 vectors in Rn, or any number of vectors which are more than n in Rn, and conclude that there cannot be more than n linearly independent vectors in Rn. One can in fact prove little more. So take u1, u2 up to uk. See, in R3 you see that it is a span of e1, e2, e3. So if you take more than three vectors in span of e1, e2, e3, it will be linearly dependent, is what we have observed. So this is more generally true. Suppose I take u1, u2, uk, some vectors in Fn, and v1, v2 up to vm, vectors in the span of u1 up to uk. Now if m is bigger than k, then this set is necessarily linearly dependent. That's the claim. So let's look at the proof. The proof is similar, the idea is similar to what we saw just now. Construct matrix A by taking its rows as u1 up to uk and v1 up to vm in that order. That means the first k rows are u1 up to uk and the next m rows are v1 up to vm. So now we know that v1 up to vm are linear combinations of u1 up to uk. Therefore rank of this matrix cannot be more than k. Now construct a matrix B by taking the first m rows as v1 up to vm and the next k rows as u1 to uk. Now this is the matrix B is nothing but matrix A with some rows exchanged, swapped, or interchanged. So therefore A and B both will have same row reduced echelon form, and therefore both will have same rank R, which means that rank of B has to be less than equal to k. Now m is bigger than k, therefore m is bigger than R. Now look at the first m vectors, v1 up to vm. They are nothing but v1 up to vm. And out of these v1 up to vm, at most r vectors can be linearly independent because the rank is r. Therefore, and m is strictly bigger than r. Therefore, v1 up to vm, they are linearly dependent. Now, suppose A and B are square matrices satisfying the property that AB is equal to identity. Now, look at the row reduced echelon form of A. Write it as E times A, where E is product of several elementary matrices. If A is not invertible, then EA has a 0 row, but then that will imply EAB has a 0 row, but that is not true. We know that E cannot have a 0 row. So therefore A is invertible. So that means B equal to A inverse is invertible, and BA is equal to identity. So what we have shown here is that if AB is identity, then BA is also identity. If you take a matrix which is not a square matrix, this need not necessarily be true. AB is identity matrix of that size, not necessarily imply that BA is, if BA makes sense. It need not necessarily be need not necessarily be an identity matrix of whatever size. Here we have an example. Take A to be matrix with rows 2 0 minus 1 and 1 1 minus 1, and B to be the matrix with rows 1 1 0 1 and 1 2. Then AB is identity matrix of 2 by 2 order 2, but BA is not equal to identity matrix. Now let's make one more observation. Suppose I take u1, u2 up to ur vectors in m cross 1 and another vector u also in m cross 1, f m cross 1. a1 up to ar are scalars, and P an m cross m matrix which is invertible. Then U is equal to a1 u1 etc. up to ar ur if and only if Pu is a1 times Pu1 plus etc. ar times Pur. So if I look at this case when u equal to 0, this says that a1 u1 plus etc. ar ur is 0 if and only if a1 Pu1 plus etc. ar Pur is 0. Or in other words, u1 up to ur are linearly dependent if and only if Pu1 etc. up to Pur are linearly dependent, or or u1 up to ur are linearly independent if and only if Pu1 etc. up to Pur are linearly independent. Now let's look at the situation that A is an m by n matrix. So all these columns of A are vectors in f m cross 1. Now if I take a invertible matrix P, then the above equation implies that if there exists r number of columns in A which are linearly independent and other columns are linear combinations of these r columns, then the same is true for the matrix P times A. The same way, if I take Q to be an n cross n invertible matrix, then we can make the conclusion that if there exists r number of rows of A which are linearly independent, and the other rows are linear combinations of these r rows, then the same is true for the matrix AQ. Combining all these facts, we can make a very nice, useful observation. We need to use these facts that we have discussed just now, and then properties of row reduced echelon form, and the last theorem that we proved earlier. Rank of A is equal to maximum number of linearly independent rows in A, and that's also equal to maximum number of linearly independent columns in A. That is same as rank of A transpose, and this is also equal to rank of PAQ for any invertible matrices P in Fm cross M and Q in Fn cross N. With this, we conclude this lecture.